Hi. First interactive question. How many were here last year? I think I see a lot of the same. Yeah, some of you are not admitting it, I think. So I will need to do some review. So you might remember in our last episode, we probably looked at a picture like this. This is kind of a high-level view of what I think is some really relevant guidance about emerging technologies. I'm not going to talk about derivation of emerging technologies or categorization or taxonomy, but I think there's kind of an important time scale here on the y-axis, and a set of technologies represented by the bars, the bluish purplish bars. The key being that if you are going to do something whose latency takes, let's say, a couple microseconds or more, you're likely to want a context switch. On the other hand, if you're doing something that is in the 200 nanoseconds or less, or maybe with a little bit of headroom, you may not have to represent any kind of pause to your application at all. You may implement something as a memory access. If you're in between, then you may not be sure what to do. You might want to spin, if you have a choice because it's not worth a context switch. You might be debating whether to integrate something as a memory access or more asynchronously. So this is kind of how I model that space. And in some cases, it's less important to talk about what technologies are in use than it is to talk about where you fall in the spectrum of application behavior relative to that technology. So that's just kind of context that kind of connects the technologies to an application view. Switching more directly into the NVM programming model, here's the what is it. Here's a pointer to the specification that Jim referred to. There are both block storage and file features, and they apply to both conventional I/O and persistent memory. This range of things are described in the programming model, but a lot of the activity, especially recently in the programming model, is related to persistent memory. By which I mean the same thing that Paul Grun was referring to when he showed memory access. The idea that it's data flowing between something inside the CPU and memory, as opposed to something asynchronous flowing the way we think of I/O. That's what I refer to as persistent memory, and I believe Paul was referring to it that way as well. We have, in the programming model, committed ourselves to the memory map file paradigm. There can be some debate, and there is research going on in the industry about other paradigms. There's also the shared memory, the SHMEM style paradigm for accessing persistent memory. The programming model commits to the memory map file paradigm, suggesting that it may be a reasonable bridge between existing applications and direct access to persistent memory by a method that's familiar, or at least although it works better than it does today when you have persistent memory. It also limits the scope of reinvention. If you choose to build up a new paradigm for accessing persistent memory, you have to deal with how are you going to manage your namespace, how are you going to deal with permissions. All those problems are already solved in a file system. And there are plenty of open source implementations available for experimenting. So those are some of the reasons why we chose memory map files. Also, it's a programming model, not an API. It's not really a language. And the reason for that is because it involves artifacts of kernels, although it's not entirely in the kernel. And if you want to span Linux and Windows, you can't describe an API directly because they'll have nuances of APIs that have to align with nuances of the operating systems. So instead, we define attributes and actions and use cases. It's somewhat similar to taking a verbs approach. So that then implementations will map actions, map their APIs to the actions and attributes of the programming model. This is still the overview. This is the iconic picture of the programming model. Here's where I'd like, excuse me. So here we're seeing an application. Make sure I get, yep, there it is, the right button, with the user kernel boundary here. And the key abstractions that are defined in the persistent memory part of the programming model are represented by these squiggly red lines. The lower one, called volume, is really just a way of discovering persistent memory ranges that represent the equivalent of what used to be a disk volume, so that you can identify a body of persistent memory that you think of as if it were a kind of a disk from a file system point of view, but then it's actually all persistent memory. You can discover those using the volume mode, and then most of the action is up here at the file mode, where you open and then memory map a file, at which point the file gets application level addresses so the application can manipulate the file as variables, basically. And that's what's represented by this line right here. Then the key element is, once you've mapped it and gotten those addresses, you now have to be careful about how you manage the persistence domain, the same concepts that Paul was referring to. In our case, though, we acknowledge that there's some kind of a sync or flush operation. And what that does is it makes sure that any volatile queues or buffers inside the CPU's write path on the way to the persistent memory are flushed so that the data eerily is persistent. This starts as a local model, which is the reverse of what Paul did, right? Paul talked about some local and some remote access and then said, I'm going to spend all my time talking about the remote access. The NVM programming model starts with local persistent memory access by applications. And we really spent time working on various aspects of a conceptually simple model that turns out to be not so simple. And then we began extending it to, how do you do high availability with that? And for that you need remote access, and that's where our agendas converge. So if Paul can solve his problem in terms of remote access to persistent memory, we will love that in the programming model, because that's how we'll get high availability from our local model, right? And I'll show you more about what we're thinking there. What have we been doing lately? We recently finalized the remote access for high availability white paper. There's a pointer to it there, the very fine print. It deals with what kind of real-time flow do you need in order to be able to recover, what kind of what are the requirements to get consistent recovery, and how can we make that as efficient as possible. In some ways this frames up a problem statement, and that's really kind of what we've been talking about now for a couple of visits, for a couple of years, is let's frame up the remote access problem statement and get the industry working on it. And the good news is that it's evident in this group, the way Paul was paraphrasing the very same types of requirements that we need. And Tom's talk will go into more detail on some of that. All right, so it is happening. We're starting to get critical mass of attention on some important topics, and that really was that's why we're talking. We've also been doing work on error handling. I think it was probably it was in Paul's presentation too. There's a big difference between storage I/O and memory error handling. You get a nice status from storage, but with memory, you get an exception, right? You're executing along, and all of a sudden, if something didn't work in memory, you'll get an exception. And even worse, if you just did a memory access, it may not actually reach the memory itself for a while, and you might get the exception later, right, when the actual write to memory occurred after it made its way through the whole CPU pipeline. So this whole scenario creates some interesting error recovery implications when applications are actually direct accessing persistent memory. So we've been doing quite a bit of work on that, as an enabler. Another important area has to do with atomicity, and we will talk a bit more at the end about the atomicity journey that we're on. We are finalizing a white paper on atomicity, and it features the PMEM library, or NVM library, I think it's also called, that's open source contribution from Intel, in which there are implementations of persistent memory data structures that have a type of native atomicity built into them, and a sort of intrinsic atomicity. It's a class of data structures you can design that way. But then if you want to manipulate multiple of those, in a single transaction, you still need some transaction constructs that surround them that are basically conventional. So that's what the atomicity paper is about, is how do you deal with this combination of sort of intrinsic and explicit atomicity when you're trying to do essentially transactional type stuff. And it turns out that being able to do transactional interaction with the local memory becomes really important when you're starting to deal with recovery from remote memory, and I'll explain why that is in a minute. So our common ground is the remote access for high availability between the SNIA programming model and this group. So let's review the map and sync. I think I've already pretty much described this, but the real problem is that sync doesn't guarantee order. What you want to picture is that the CPU's got a write pipeline on its way to memory, and let's say you're using an NVDIMM, so the memory, the DIMM itself, is the persistence domain. Once it reaches there, you're guaranteed you won't lose it, guaranteed if power is lost. And it's approximately as good of a guarantee as a disk drive, right? Even with a disk drive, there are ways you could still lose your data. So we didn't really raise the bar on that with just an NVDIMM, but imagine the CPU has a write pipeline, and that write pipeline is getting full, and it has some policy that it uses to flush things out of the write pipeline on its own, which is not necessarily the order in which they came in. It can do better than FIFO on its write pipeline. But the problem then is that even if you do a sync and flush the CPU pipeline, some of those writes will have been flushed earlier, and some of them will not get flushed until you ask it to flush, which means that there's no order guarantee associated with the sync. All it guarantees is that by the time the sync is done, everything you wrote up to that point in the range that you synced will have reached persistent memory, but you don't know in what order. This creates a kind of interesting abuse. If you want to do something atomic, then what you do is you write a bunch of data that will be subject to the update of a single pointer, let's say, and then you sync, and then you update the pointer, and then you sync again. Right, so that you know that critical section, that critical update, that commit point, was isolated, and in order to make that atomic, you need a property of that update to that thing, which we refer to as atomicity of an aligned fundamental data type. It turns out that most processor architectures actually provide you with that, some form of that atomicity, but they do it in an architecture-specific way. All right, so part of the story here is to get consistency, you probably need some degree of atomicity, and there are ways to get that locally, but now how do you do it when remote access is involved? All right, and that's where the deeper parts of this white paper come into play. So to model that, we imagine that we have, an application that's using our programming model, and the operative, we've got the load store access here. We presume that we're already memory mapped in this picture, and then we have a couple of libraries here. There's a traditional map and sync library that's already part of POSIX, so it might be in your libc, and we've also created an extension that we call optimized flush, which is similar to a sync, except it involves multiple memory ranges, and it's designed to be able to occur entirely in user space. The user space kernel space boundary is down here. So then what we do is say, okay, we've got a file system because we are using memory map files, and we'll presume that for high availability we have a companion file system, which we've drawn here as showing this network file system client using an RNIC to talk to another node, peer B, peer A and peer B. This may be a new Dr. Seuss thing, I don't know. So these two file systems are coordinated so that they, let's say, are mirroring each other, starting with the simple case. And furthermore, they're able to set up an RDMA connection session in such a way that once a file is memory mapped, there is a way to ask for RDMA to occur such that the data that was written to blocks of that file can be RDMA'd, or byte ranges really can be RDMA'd to peer B, where they'll land in the same file in the same place on the other side, right? The file systems can orchestrate that. All right, so the operative part is what has to happen during that RDMA. This is what has to happen. So this is the second of 3 views of very similar stuff that you'll see in 3 successive presentations today. I'm not sure what Tom's view looks like, but Paul had a sketch of some similar stuff. But from the NVM programming model's point of view, you've written some data. This is the application's written some data on peer A, right? And it does an optimized flush, which is an action that's defined by the programming model. And as a result, what it would like to do is a series of RDMAs of the ranges that it has to have flushed. First, it flushes them locally, which was the original definition. But now I want to make sure they're also redundant. So, I will try to use RDMAs to flush them remotely, and the RDMAs may get acknowledged, which means nothing from the point of view of the persistence domain. This is the same point Paul was making. Eventually, that means I have to say something more, and here I represent that as an explicit flush. Another round trip, besides whatever RDMAs I did that flow nice and concurrently, I now need a final thing that says, make sure all that reached the persistence domain, and I represent that here with this magic lasso. All right, this is something that's not in a normal ladder diagram, but it says that this flush operation, which may, if you implement it today, you pretty much had to talk to the remote CPU in order to do it. But what it does is make sure that all those things were reached persistent memory, and then the flush can finish, and then the optimized flush can finish. All right, so this is one way of viewing, from the point of view of the NVM programming model, the kind of activity that has to happen in order to get remote access for high availability. All right, so this frames, this isn't the only way it can happen. It's a conceptual representation, and the community is now working on ways of actually realizing this that are fairly efficient. It's true we could do it this way today, but wouldn't it be nicer if we could keep the CPU out of the loop, perhaps? If we could do it more efficiently. We're trying to run at memory speed. We're trying to get hundreds of nanoseconds, to make our writes persistent. All right, but when you run into something like this, you get into microseconds. Can we keep it to a very small number of microseconds? How close to 1 can it be? So, every time you ask for this, there's this cost to high availability. How much slower than memory speed does that cost have to be? All right, so that's really the challenge in terms of the runtime, what happens in real time for high availability. Now, what about recovery? The applications have to recover in ways that are consistent. And I think this is something that folks here would generally understand. The consistency, though, is an application-specific constraint. So, in a way, to get really good consistency, efficient consistency, you need the application to be involved, in some way to, express where its consistency points are. Now, in high-performance computing, this can be very, very coarse-grained. But for other applications, it may have to be relatively rapid. So this is where, I'm not going to go over all of the concepts that I list. Oops, I'm going to go over more than that. But I want to highlight this guy right here, that it really helps if you can express higher order consistency points, such as if you have implemented transactions. And if you can come up with an elegant way of using, flushes to persistent memory in the context of transactions, then you can establish a series of consistency points and make the whole flow more efficient. This may be similar to what we do in disk arrays with disaster recovery, right, where we have disk array speeds on tens or hundreds of milliseconds, and we have a remote site, that's hundreds to seconds away. So we create an asynchronous stream of data that's going to the remote site, and allowing it to recover to recent consistency point that is governed by a recovery point objective, which basically says, how much work are you willing to lose in the event of a disaster? So this is operating on sort of timescales of seconds, right? And these solutions exist today. What we want to do, perhaps, is run one of those solutions at 3 orders of magnitude faster, or perhaps more, so that you're using memory speed workloads going to places that are only a microsecond away, but using consistency points in order to basically speed match the stream, all right, for recovery purposes. So now what you picture is that if there's a failure, the application is not going to be able to just execute the next instruction. It's going to have to recover from a recent consistency point. All right. So that leads me to this table. In the white paper that we've released, we envision several kinds of recovery, and those are listed here under the scenarios. It would be nice, and what people would normally think of is, how about I have inline recovery? Inline recovery says the application got a memory exception, and there was another copy of the data that was consistent enough and nearby enough that it could be written into the memory location that the application was trying to fetch before, during an exception. And when we return from the exception, it's fixed, right? Now, so that's inline recovery. That's the best kind, right? Down from that was what I would call backtracking recovery. This you'd picture as rolling back transactions to a consistency point and resuming execution from there. All right, that's backtracking. And you need a consistency point, and you need an application if you're going to use that kind of backtracking that can do that, right? And resume from a known consistency point that is hopefully very recent. The next level is that you have to restart the local application, either because it doesn't know how to implement backtracking any other way, or because something forced you to reset your server, right? And you're in a high availability environment, right? So you have to be able to handle that. Or maybe your server failed, and along with your server, one of your copies of all of your persistent data failed. Right, and in that case, you have to do a failover to a nearby server that has the other copy as of a recent persistency or consistency point, right? So then you can talk about under what circumstances can I do each of these methods. And it turns out that if you want to do inline recovery, the sync guarantee is not sufficient. So if what I've been doing is streaming my data to a remote site asynchronously, I can't actually do an inline recovery and resume from the next instruction because the data that I've made that's redundant is too out of date. So the inline only applies if you're doing local redundancy. All right, it's possible to do local redundancy with that level of consistency, but really not remote. It's not really feasible. When can I do backtracking? Okay, now that depends on what kind of exception I have. Precise exceptions are those where you know what instruction it was that experienced the error, and contained exceptions are ones where you know what memory address it was that experienced the error. This is a slight oversimplification of the model, but you can imagine that you have to know both of those things if you're going to do inline recovery. If you don't know the instruction, you might be able to do backtracking recovery as long as you know the location. But if you don't know either, or if your application can't do backtracking, you're going to have to do a local restart. Or obviously, if you were forced into a restart for some other reason, or if you lost hardware, then you have to do one of these more extreme things. All right, so it's important to think about the consistency model for recovery when you're setting the rules for the real-time activity that has to occur in order to support those. And especially, I want to continue to seed this idea that having a recovery point objective in play involving a series of consistency point is a likely way of making this whole system efficient enough to actually work. Finally, last year when I gave this presentation, I talked about atomicity, and I said, well, we have this idea of atomicity of a fundamental data type, right, which is supported by the processor architecture. And somebody said, well, what if you're working across processor architectures? And, the problem gets harder. And then somebody said, well, how about if we have atomics, right? How about if you use atomics for this? Okay, now you have to say atomic with respect to what? Right, because the atomics we have are with respect to runtime, respect to other processes that are running and need to see a consistent view of the data. Right, atomics facilitate that, the ones we have. The problem is that's the wrong kind of atomicity for this. I need atomicity with respect to power loss. Right, so the atomics we have are not actually designed to provide that kind of atomicity. If you want to provide that kind of atomicity in a remote site, the only party who can do it is the party that's on that remote site. The first guy there is the remote RNIC, right? The peer B sync RNIC. All right, so if you want any kind of remote atomicity, that party is going to have to be involved because it has to involve the way that party gets its data into the persistency domain such that it is atomic with respect to any power loss that could occur there. All right, it either all happened or not, or none of it happened when you come back, when the power comes back, right? So it has to involve the remote RNIC, because it's the only guy on the scene, right, that has any chance of achieving it. So then you say, okay, how would I have to enhance some protocol? And this is really exploratory stuff, right? This is just a thought table. Right, how would I do that? Well, I could say, well, I do have some atomics right now, and what I want to do is add power fail atomicity to my real-time atomicity, primitives. All right, well, that would be one way. Another way would be to say all RDMA writes are atomic. Right, that's pretty expensive, not very selective. Right, so now you can see I've started an experiment with some criteria. How good are these alternatives relative to each other, and some kind of a ranking based on some criteria, like, how much overhead does it create? How much can I focus on the things that really need to be atomic, and how compatible is it with either RDMA or the existing NVM protocol specifications? So I could say, okay, either in addition to the requirements for existing atomics, or all RDMA writes, or RDMA writes in a given session, or RDMA writes based on some flag, right? I'm messing around with all kinds of protocol here. A bunch of this is probably not a good idea. It's just an experiment, a thought experiment, right? So how do I achieve remote atomicity? The default is the bottom one, using checksums. Right? If you don't actually have any hardware atomicity, that's what you end up doing, is using your own checksums on all your data so that you can tell if something broke, right? Something tore, right? So this is just the very beginning of a new thought thread that says, given that applications need some form of power fail atomicity at their remote site for consistency, how would you even go about building that up? So that's what we've been working on lately in the persistent memory programming model. There are a couple of other interesting things I want to mention. I showed that diagram of a flush that showed the RDMAs for everything I'd written lately going out at once. That may not be the most efficient way to do it. So we're continuing to work on models for that. How might you involve the application in order to create a more continuous stream, of that type of activity, so you're not inadvertently making it more bursty than it needs to be. So that's an example of ongoing work. There's a bunch in error handling as well. So that's what we've been doing in the programming twig, and I think you can see how it relates to the same types of issues that this group has for remote access to persistent memory. Questions? Paul has a question.
Could you roll back to slide 8?
8?
Yeah.
Oh my, he wrote down my slide numbers.
No, I just noticed this one.
You noticed something?
So the two peers there, let's assume for the moment that those are two storage controllers, which is kind of the model you're talking about here, right?
They're servers. They're two servers.
Yeah. Okay.
They're not storage controllers. They're servers.
But you could have two storage controllers which are implemented as servers, right?
I could have servers implemented as storage controller too, but let's go on.
Right. What I'm trying to make there is that they're in an HA case, and I'm speaking on behalf of another guy who sits in the DSDA group who unfortunately can't be here this week. But anyway, they have a case where they have two controllers that are in an HA configuration, and they communicate over a backplane or a PCI Express as opposed to RNIC. Does that have any fundamental impact in what you're talking about here, or is it just the fact it's a different wire that... So in other words, what connects the two, peer A and peer B, isn't Ethernet?
Let's see.
as
So the
traditional
simple
here?
answer is that no, it does not have any fundamental impact. It's
Okay.
just a different wire, and it's got the same challenges about how to get remote durability if you're going to the memory system on the remote site. But there have been other presentations that show that the situation, if you're going to a PCI device on the remote site, the situation's different because you don't have that darn CPU in the way caching a bunch of volatile stuff.
Okay.
All right, so, you know, the answer is it doesn't really change it unless, right, you twist it.
Yeah, I just want to know which, you know, what monsters in the swamp we're looking for, so.
It does alter the atomicity guarantee in the failure case because it will have synced to, you know, peer A. Peer A may not yet have synced to peer B. So there will be an additional complexity in the recovery. But that's entirely the domain of the server. The API, if you will, the NVM programming library, presumably would not have received the commit response. Therefore, the data is indeterminate.
Yeah, that's the way I would have read it as well. I just want to make sure I'm on the same page.
Yeah,
Thanks.
I thought you just substituted, you know, PCI for an RNIC.
Well, that was the original
Right,
question.
which was the question, right?
Yeah.
But then we talked about the NVMe protocol, which has other considerations.
Right. Thanks.
Hi, Doug. Can you roll back to slide 9?
Sure.
Yeah. So I was looking at this slide, and you know, if you you know all these many write operations on the rightmost line, in the remote writes that are happening, you know, various.
Yeah.
Okay. So if you take this picture, and if there is a failure on the sending side, then if you move back to your slide 12, so I think any of these options that you have chosen will still result in a fractured block.
More is required, right? The application has to structure itself so that it does a bunch of disposable activity which commits as a result of an atomic write. All right, so that's the additional requirement that I wasn't very explicit about. Right. So then you have to do a pattern of flushes and atomic commit that makes that consistency rule true. Right. So you're right, it can still tear unless the application is structured in a very specific sort of transaction-like way. Right. And then even then if it tears, what you do is because you've got atomicity as a tool, right, you know where to roll back to. Right. You can have commit points at the remote site.
That means, you know, you will probably have to have, you know, you're not writing in place, you're writing out of place.
That's right. Disposable stuff is not writing in place. Yep.
Yeah. Okay.
We didn't break physics.